Today we move on to a very current topic. Superconducting qubits are some of the leading solid-state qubits, and we were building up to this topic in the last couple of lectures with superconductivity and superconducting devices. So this will all come useful in this lecture. I will give you a small refresher. I'm grateful for slides to Professor Hans Moy on slides on flux qubits, to Andreas Wallraff introductory slides, and charge qubit slides, and Alexey Ustinov for slides on phase qubits. Those are three very different conceptually quantum states, but the circuits look very similar. So this is a very interesting trichotomy in the field. Three different quantum states, but essentially one circuit. And Britton Plord also gave very nice data on flux qubits that I will show you today. The proper framework to think about, well, in principle, any qubits, but especially superconducting qubits, is to think about electrical circuits, like the ones built from capacitors and inductors and resistors, but operated in a quantum regime, such that quantum fluctuations, quantum coherences, superpositions of states become relevant. And we already discussed in this course how you achieve that, and I will show you what that means for superconducting circuits. But at this point, you should have some intuition that you can start with a semiconductor device, a metallic device, and if you maybe cool it down and isolate it well enough, it will start behaving quantum mechanically. So this is the idea here, and the two different ways you can see coherence is one is maybe a superposition of charged states, so shown here by an electron being on the bottom plate of a capacitor and the top plate of a capacitor, and that is maybe going in the direction of charge qubits. The other thing that you could see is a little bit more bizarre, but if you cool your circuit low enough, you might be able to see a current flowing through the inductor in both directions at the same time. So here, this picture shows a bunch of electrons, 1 billion maybe, traveling clockwise and counterclockwise at the same time in a quantum superposition of the two directions. And the two represent the charge and the flux. I showed you in the last lecture that in this Josephson Junction model, there is an analogy between charge is analogous to a coordinate, and the phase or a flux is analogous to a momentum. And so in the quantum limit, there will be an uncertainty relation between charge and flux. They will be related by the commutation relation in the quantum mechanical terms. So there is an intimate connection between these kind of superpositions and these kind of superpositions in the circuits that we will discuss. Even though here there are no Josephson junctions, and I derived this for you or motivated it for you for the case of Josephson junctions, this is much more general than just Josephson junctions. This is a true for just throughout the quantum mechanics, that these are two conjugate variables. Okay, there is a very good motivation to indeed use superconductors to go to the quantum limit of electrical circuits. And the primary reason is this superconducting gap. Superconducting gap, remember the gap around the Fermi level, ensures that there are no intermediate levels, excitations, in a piece of superconductor up to the gap. And what you want to do in a superconducting qubit is take a two-level system, the qubit, and put it inside the superconducting gap. So whatever this two-level system is, if it is inside the gap, it is far separated from all other levels. And for that reason, it is not coupled to other degrees of freedom. Just a refresher for you, superconductivity made up of Cooper pairs. This pairing is characterized by this energy gap. So to break a Cooper pair, you have to pay this gap. Yeah. And if you have a piece of superconductor, it is characterized by a macroscopic quantum state, a wave function. So it's a really quantum object, a superconductor. It's a wonderful platform to build qubits. And if you have two pieces of superconductor, you can have Josephson effect, supercurrent flowing in between. And if you have a superconducting loop, the wave function of a superconductor, this macroscopic order parameter, will be quantized around the loop. And that means that there will be a phase condition. Phase has to always amount to 2 pi. Or because phase is very closely related to flux, there will also be flux quantization in such loops. So this is just to refresh what we already studied. Now, what is the simplest quantum circuit you can try to build? You could try to build an LC resonator. If we tweak the values of L and C, we could get the resonance frequency of this resonator to be in a gigahertz regime. This is experimentally very convenient. Not too small to enable fast control, not too large because high frequencies, very high frequencies are difficult to generate, but something around a few gigahertz is routinely possible in the lab. So this does not come out of nowhere. And you all know how to solve this problem, but you also know that this is analogous to a harmonic oscillator. Right? And in the harmonic oscillator, there are quantum levels which are described by this spectrum. And one peculiar thing about them is that they are equidistant. So the distances between all these quantum states in a harmonic oscillator, 0, 1, 2, 3, 4, etc., are the same. Now, for qubits, that presents a problem. Because imagine we apply this 5 gigahertz frequency, the energy level distance between the qubits, and we start on the ground state, but we apply this frequency to induce a transition to this state. But it might as well jump over and go to this level. We might be creating superpositions of all these states, because we cannot distinguish which transition we are driving. We're driving all transitions at the same time. They're all equidistant. So this is more analogous not to a spin 1/2, which only has 2 values, and you cannot drive it to higher levels because there are no levels. This is more analogous to a photon, to quantum states of a photon in some cavity, for example. You can have photons are bosons, and you can just populate them indefinitely. So this is an electronic photon. In order to make a qubit out of a superconducting circuit, you have to make the energy level distances unequal. And that you can do if your oscillator is not harmonic but is anharmonic. So if the bottom of the potential is a parabola, all the levels will be equidistantly spaced. That is the case in an LC circuit. But if the potential is some other function, the energy level spectrum will be different. For example, a square well potential would give you, like in a particle in a box problem, right? The different level spacings. So that's one example. Turns out Josephson junctions are perfect for creating these unequal level spacings because they are anharmonic. They are nonlinear. Remember, the IV of a Josephson junction is highly nonlinear. There's a supercurrent, no voltage for a while, and then there's a switch until it finally goes into a linear regime at high bias. So this is a way to create a qubit out of a linear circuit, to put a Josephson junction in this circuit. To remind you what that is, 2 pieces of superconductor and the 2 wave functions in the 2 pieces overlap. And the important parameter is a phase difference between the 2 wave functions, phi1 minus phi2, phase difference of phi. Then for this phase difference of phi, there is a Josephson relation. In the simplest case for tunnel junctions, it's a sine function. Critical current is an amplitude. And so as you apply bias current to the Josephson junction, phase winds according to this cosine function. You can store energy in a Josephson junction. This is the maximum energy you can store, but for every given phase, Josephson energy is a cosine function of phase. We discussed this circuit diagram that the Josephson junction is represented by this cross, and it's an element that has this dependence, but there could also be a capacitance here, resistance, and that's an RSJ model that gives you a washboard potential. And that's from the previous lecture. A common technology for that is an overlap shadow technique. You can see here two pieces of aluminum evaporated like that and like that, making an overlap, a Josephson junction, and in between we oxidize to create a tunnel barrier. So this is the direct implementation of this diagram. Now let's go back and ask what is the inductance of this circuit? Well, inductance is defined as if you change a current at some rate, di dt, what will be the voltage? Yeah, that's the proportionality between the di dt and voltage. Or you can calculate inductance from how much energy is stored in an element if you flow a current. Yeah. And whatever you do, I'm not going to go through the math here. You can look it up on in Tinkham or even on Wikipedia. But whatever you do, if you do a derivative of current or if you calculate the energy, you will hit these sine cosine functions. So this is why it's nonlinear. And if you consider only small biases, you can write down Josephson inductance like this. So it depends on the current that you bias the junction with. So this is really nonlinear. It changes for a bias. Yeah? So in an inductor, inductance is just given and independent of the current. Here it's not the case. So now replace the inductor in this LC resonator with a Josephson inductor with a Josephson junction. Here is a more rigorous formula, by the way, for the Josephson inductance. This one has the cosine, and this is what you have to do in terms of phase. So inductance is related to di dt, but di dt for the second Josephson relation is like d charge dt, which is a second derivative of phase in time. So you can rewrite in the end inductance in terms of phase. So it's nonlinear. Very schematically, if we now write the energy levels for such a LC circuit, the energy levels will have different spacings as you go up. And so we can just take the two lowest levels and say that this will be the ground state of our qubit, of our circuit, and this will be the excited state of our circuit. Now if we apply microwaves at this transition frequency, we can induce this transition, but all these other higher transitions are not excited because the energy difference does not match. So this is now, this subsystem of this circuit becomes analogous to a spin 1/2 particle. So those were the concepts for how to understand quantum mechanical electrical circuits. In order to actually work with these circuits, you have to fulfill fairly stringent experimental conditions, but not very different from other examples that we discussed in this course. Of course, you need to cool down to low temperatures to avoid thermal population of these higher levels. And you can calculate what are these other spacings, how much energy you have to get to go there, and you have to cool down below that energy to avoid coming to this level, for example, by temperature. But also because this is an electrical circuit, not only can this circuit be excited by temperature, but also by any signal that comes and couples to this circuit. For example, a noise from the environment, any AC fields from your cell phone, from an elevator moving somewhere in the building, from cars driving down the streets, all of those things create magnetic fields. So you have to shield your experiment. Even fluctuating fields from things you don't think about can cause problems. You walking, you talking in the room creates vibrations and magnetic fields that these circuits don't like. They are extremely sensitive. And the quantum mechanics in them is extremely fragile. So there is this schematic box, which when you are in the box, you're protected. The box can be a metal shield, a magnetic shield, filters in the lines. You can put capacitors to avoid direct coupling through the wires that you send to the resistor, to the circuit. The other important thing you have to worry about is that if the circuit has some resistance, it will dissipate. If your superposition is charge or current, leaking through and giving away heat is equivalent to loss of information, certainly loss of quantum information. So here superconductivity comes in actually handy and suppresses dissipation. You have to, of course, build circuits to interrogate this qubit and to control it, but they have to be coupled not too strongly to not destroy the states that you're working with. And you can already see, because we have these coaxes and these capacitors here, that all the experiments that are done in the lab are high-frequency experiments in the microwave domain. So a lot of microwave engineering going on. You have to design waveguides, you have to design your circuits, and think about all the signals that you are measuring in terms of waves that travel down the wires rather than currents and voltages that you apply. So you have to develop high-frequency intuition for doing all these experiments. Okay. So remember 3 types of qubits. Well, this slide explains 2 because they are related by this conjugation relation, by the uncertainty principle, and very simply illustrates how you go from one to the other. You just simply have to change the ratio of the charging energy in the Josephson junction to the Josephson energy in the Josephson junction. And you go from charge qubit to flux qubit. In a charge qubit, where charging energy is the important one, it also sets the nature of quantum states that you can create. In a charge qubit, quantum states will be charge on this island. So for example, a charge there or not there. And of course, in practice, it is a big piece of metal from the point of view of a single electron. You can have an Avogadro number of electrons there, but adding just a single Cooper pair costs you charging energy. And so having that extra Cooper pair there or not creates 2 states, the ground state and the excited state. Flux qubit, also very easy to understand what that is. It is a loop, and the 2 quantum states are current traveling left and right in this loop, or a flux pointing up or down. Like a spin pointing up and down. Here we have flux. As opposed to spin, this is created by a billion electrons. So this is a very bizarre macroscopic quantum degree of freedom, collective of billions of electrons. But it is described exactly like a spin 1/2 particle. Now to do that, if we put a lot of charging energy in this circuit, the current will not be able to flow. It will get stuck in these superconducting islands. So we have to drop that, and we have to have a large Josephson energy to create a barrier between current flowing left and right, to create an energy barrier in between. These are some of the pioneering papers in the field. The field has moved quite a bit farther, but if you want to go to the roots of these qubits, read these papers. They're classic by now, beautiful papers. And here are the pictures of the different qubits. These 3 are all the same technology, this aluminum shadow evaporation. And the primary thing that changes going from here to here is exactly the ratio of Josephson energy to charging energy. And you control that by making the junctions different size. So in this circuit, this little bar is the island. Is the island on which we keep the charge. And these two guys at the overlaps create the tiny, tiny Josephson junctions. So the Josephson junction is small, Josephson energy is small, the charging energy is large. There are two of them for an interesting reason, because now we have created a loop here, and that is like a little squid. So applying flux through this loop changes the Josephson coupling of this circuit. So Josephson coupling becomes tunable because we have a loop. We don't have to fabricate an infinite number of circuits until we get the ratio of charging energy to Josephson energy right. We can just make a loop and tune it in situ. There is a coupling to a charge sensor, which is a SET, single electron transistor here. So that's the readout circuit. Flux qubit must have a loop for flux to flow left and right. This is actually the readout squid I'm pointing at. This is the qubit. It has several Josephson junctions here made by shadow technique. And this is the readout circuit, which is another squid that measures whether current flows left or right. This is a hybrid, this kind of in between flux and charge. So the ratio of Josephson to charging energy somewhere in between. And this was a very clever experiment early on where they found the sweet spot between flux and charge where they were protected from decoherence. Turned out that it's very difficult also to tune the qubit when you are protected from couplings to environment. So this is now replaced by a slightly different version of this qubit. This one, the phase qubit, we will talk about later. It is based on a different technology. This is a niobium tri-layer technology. You don't see much in this picture, but I'll show you different pictures later on. Okay, once again, the same experiments lined up on the scale of Josephson energy to charging energy. It gives you some numbers this time. So Josephson energy over charging energy, a factor of 100 different. So charging energy much bigger. That's the charge regime, charge qubits. And here, flux qubits, we are a factor of 1,000 on the other side. So Josephson energy dominates. And that was that peculiar regime in between, which very interesting experiments from Saclay, for example, were done here. Phase qubits are off the charts here. This is actually remarkable because I didn't tell you what phase qubit is, but this is done in huge Josephson junctions, micron size. You can just completely forget about any charging energy, and the quantum states are a little bit counterintuitive, but we will get there and you will see. These are some of the coherence times. This is a snapshot from a little while ago. All of them have gone up somewhat since then, but we can see that pretty early on people were able to get into the microsecond coherence times for these circuits, which, if you think about it for a second, is quite remarkable, because this is now a physical electrical circuit, very big from the atomic point of view, and we are applying currents to it, microwaves to it. We are creating coherent states in that circuit on a chip, very strongly coupled to environment. It has inductance, it has capacitance, so coupled to charge, to flux. And we are able to isolate it so much that we can, on a fairly long time scales of microseconds, see quantum mechanics in play in these macroscopic circuits. This is a graph that reiterates what I said. Here David DiVincenzo plotted the progress of coherence times versus time. The first experiment down here on the charge qubit done by Nakamura, several decades down, and then rapidly, by learning how to isolate circuits better, which materials to pick, this community have achieved remarkable progress. You could say this is a Moore's law for just the coherence time. Of course, remember there are 5 DiVincenzo criteria, and this is only one of them to have a very coherent system. You have to also be able to read out and initialize. They can do that pretty well. You also have to be able to scale. You have to be able to create 1 qubit and then make more and more 1,000 qubits to build a quantum computer. And this is why, in particular, these circuits are so interesting, because it is the easiest thing to do is to scale this up, because all you need to do is just print these squids on a circuit and make 1,000 of them. So if they're coherent enough and coupled strongly enough, scalability is really a strong feature of this approach. And so if we can get the coherence times up, and this looks very optimistic, then this could be actually a winning implementation for a quantum computer. This line here, I will talk about in one of the future lectures. You have to be above this line to do quantum algorithms, but the specific thing that you should be able to do when you're above this line is called quantum error correction. So a code which tracks down the errors, dephasing, decoherence in your circuit and flips back the qubit. So this is a very important line, and we have to be above this line for an individual qubit. And a quantum operation in these circuits is extremely fast. They estimate several tens of nanoseconds, similar to semiconductor qubits, very fast. And for these data points out here, for the latest experiments, this is many, many operations, many thousands of quantum operations that you can do. Okay, so this was my introduction, and now we are going to talk about flux qubits, charge qubits, phase qubits. Flux qubit, it's a loop with 3 Josephson junctions. Conceptually, you would think you only need 1. A loop gives you an LC circuit, and add 1 junction to create anharmonicity, nonlinearity that you need. Turns out, for practical reasons, it works better with 3. These bigger junctions, 1 and 2, they are, you can think of them as kind of largish inductors, so they eat up inductance. You don't have to make such a big loop. And this small junction creates the tiny potential wells that define your quantum states. This is just a classical slide to show you the energetics, the potential landscape in the squid. First of all, flux quantization applies, and so the sum of these 3 phases must amount to 2 pi. You can also add the external flux to this circuit. And that means that you only have 2 independent degrees of freedom, because the flux on the 3rd junction can be just expressed in terms of the flux on the other 2 using this expression. If you want to know the energy, you have to add up the energies of the 3 junctions, the Josephson energies. So we have these cosine functions, 1, 2. And for the 3rd one, we have already substituted the phase of the 3rd junction in terms of the phases of the first 2 junctions. So then you can plot this, this energy for phi 1 and phi 2. This will be a 3-dimensional map. And because you have 2 cosine functions in both directions, there will be these oscillating maxima and minima. And the way to operate this qubit is to go along this line. And along this line, you're going to have a couple of minima. So this is a cross-section along this line. The inductance of this loop will make the minima go up and up. So at the lowest state, you will only have 2 minima. The meaning of this line is also very clear. That is the external flux that you apply. And then the 2 phases, if the junctions are exactly equal, will wind together. So now I have translated this notion of a qubit into what exactly are the quantum states. The quantum states are these 2 potential wells, left and right. And the meaning of these 2 wells is when you're here, the current in the loop is circulating clockwise, and when you're here, the current in the loop is circulating counterclockwise. That's the classical perspective. We can also solve Schrödinger equation in this potential. And we will have always two lowest energy states. Detune the two wells by a little bit, and this detuning is a flux. So just apply a little bit of flux to make them unequal. We will have two solutions, one with a maximum in the right well and one with a maximum in the left well. And one of them will be lower in energy because one of the wells is lower. So this is just saying that if you apply a flux to that loop in one direction, current will be flowing in a direction determined by the flux to screen that flux. And if you apply flux in the opposite direction, you will tilt it the other way around. Now the important point is that the symmetry point of this potential, this situation, is not when the flux is 0, because then also there has to be a minimum at 0. This is around the point when the flux is equal to half a flux quantum. So the symmetry point is flux equal to half a flux quantum. At the symmetry point, the two solutions have equal probability to be in the left and the right well. So whatever energy level you are in, you are flowing kind of left and right at the same time. There could be an energy splitting between the blue and the red, and those are the two qubit states. And that would be because of this tunnel barrier. So the two wave functions are coupled, and there will be some exchange splitting between the two. So now I expand really around this degeneracy point, half a flux quantum. And I see that there is an anti-crossing between the two levels. And as I tune to the right or to the left, the two energy levels split. So in fact, the blue one comes down and the red one goes up, and they go through this anti-crossing. And these arrows show the directions of circulating current. Now, how do we measure this? Well, we need to somehow detect whether the current is flowing left or right. Those are the two states. So what we have to do is build a magnetometer around. And the magnetometer is another squid. So it's the same technology, and the difference between the inner thing, which is the qubit, and the outer thing is that these junctions are much bigger. So this circuit is not quantum. It's in a different regime. But it can measure flux. So then we also need to control this qubit, and that we do with microwaves. Remember, we tune the parameters of this circuit such that these splittings correspond to some gigahertz frequencies. So we have to apply microwave signal. And when the microwave signal is on resonance with this energy splitting, we will start inducing transitions. So this is now a plot of the signal on the detector. This signal, if it's high, it means the current in the qubit is circulating left, and if this signal is low, qubit is circulating the other way. And now when we sweep the flux through this loop, and we are on resonance with the microwaves, we see that we start having transitions between circulating this way and circulating this way. These are these two signals. So that's a microwave spectroscopy of a flux qubit. This slide reiterates some of the same points, but what I want to show you is once again a picture. This is the first device that they've built in Delft, and here you have exactly what was in the previous slide. A qubit is the inner loop here, and these little breaks here, here, and here are the three Josephson junctions of the qubit. And very tightly around it, there is a second loop with just two junctions, and that's the readout squid. So the way you measure is you apply current through the outer squid near the critical current. And then when the flux switches inside the loop in the qubit, you may induce a switch in the measuring squid. So then you know that the qubit flipped. This data from John Clark's group in Berkeley shows the spectroscopy of a flux qubit. Now these lines are as we sweep the microwave frequency versus flux. So there has to be a resonance when the two frequencies match, the distance between the levels and the microwave that we apply. And so we get these resonances. This is very similar to spin resonance. Right? When we are on resonance with Larmor frequency and the microwave frequency, we start inducing spin flips. This is exactly that. When we are on resonance with this qubit transition, we start flipping the current from going left and right. So the remarkable thing about this data is that the energy level drops, the energy difference goes down, but here at the symmetry point, in a classical circuit, the energy levels should become equal. So this point should just go to 0. And they don't. They show this anti-crossing. So this is the first evidence I give you of quantum mechanics in these measurements. Because the coupling between the current flowing this way and this way induces this anti-crossing, and that is the first proof that this circuit can work as a qubit. And this is, of course, the ultimate proof that this is a qubit. Rabi oscillations. Remember Rabi oscillations? We apply a microwave pulse for a given time, and we can induce a rotation of spin from up to down by any angle we want. Depends on when we stop the microwave pulse. And then our readout will oscillate between up and down, up and down, up and down. So in this case, our readout will oscillate between current flowing left and right. And for flux qubits, they achieve already quite remarkable results these days. You can see many of these Rabi oscillations, and they're very fast. So in 1 microsecond, you have many tens. And the coherence time, it looks like it will allow it to go for even longer. So this is a very good starting point, and you can do many quantum mechanical experiments with this system. You can repeat almost the entire repertoire of quantum AMO experiments, so experiments done with single ions. All the quantum tricks you can play there, you can play here as well. This is really like a quantum ion, but it's a macroscopic one. It's an electrical circuit. And just to reiterate that this is an electrical circuit, these are just the designs that they went through in Delft over about a decade. They've been trying to improve the coherence times, optimize the readout, make it single shot, make it non-demolition, couple 2 qubits, and they went through iterations of the circuit, but all they had to do is rewrite their design and make a layout difference. So for example, going from here to here, they went from having a separate squid for readout to integrating it like that and sharing these stream of junctions between the readout and the qubit. So it became one circuit. It gave them better results. Here, 2 qubits are coupled. There are 2 sides. And they went into this topologically inverted design to protect from some noise. If there is a uniform magnetic field noise through this circuit, it would couple equally to this side of the loop and this side of the loop, and those 2 fluctuations will cancel. So it's called Radiometer setup, and it helped them protect the qubit from oscillating magnetic fields. And then finally, this circuit looks even more complicated, but what that allows them to do is to now tune the 3rd junction in the loop. Remember I told you if you have a squid, you can tune the Josephson energy between these 2 nodes. So they went for their qubit from 3 junctions to 4 junctions, and now applying a flux here, they can modulate the 3rd junction. And they can make the gap, the anti-crossing gap, tunable. So it's like an artificial atom, but you can completely rewrite it if you like. Okay, that was flux qubit. Now phase qubit. Phase qubit, I really don't have an analogy for you to think about. I cannot tell you it's a current flowing this way versus that way. Its phase is the degree of freedom in this qubit. So I'm just going to tell you how it is. you have to remember my washboard potential. Remember, for Josephson Junction, if we write all the equations in terms of phase, the energy landscape is this infinite ladder of potentials going down like a washboard. And when we are in a supercurrent state, we're trapped inside one of these potentials. And when we're in a finite voltage state, we're running like a ball through these potentials. So now we focus inside one potential. So it is a potential. It is a trap. And we can solve Schrödinger equation in this trap. And we can get some quantum levels in this trap. This is not a harmonic trap because this is created by a cosine function oscillating. So this has all the properties we need, the nonlinear Josephson inductance. And so we can just say, okay, the lowest level in this potential will be our qubit ground state. The higher level will be the qubit excited state. And the other levels have different energy spacings. So when we apply our microwave pulse, we don't talk to them. They don't matter. So all we need for this qubit is just one Josephson junction. The size don't matter. In fact, they work with very large ones, no charging energy, macroscopic junction. And what are the degrees of freedom? Well, it's a phase difference between these two plates. But it is actually always the same phase difference because we're always on the same axis. So it is a quantum levels of phase in this potential. I really don't have an analogy. That's what I have to tell you. But it is a very important qubit that enabled to realize many wonderful experiments. Now, this qubit is different in terms of how it should be operated. For example, this is the readout scheme of this qubit. Turns out, if you're in the ground state of this qubit, it's very hard to escape from this well. And if you're in the excited state, you can tune it such that escape is very easy. In fact, in the practical experiments, the two rates are different by 3 orders of magnitude. So that's just because you can just have two levels in this well, so you are tuned pretty far. And this potential is very shallow, so very easy to escape. But this one is already fairly deep, and the rate drops exponentially. Now the readout would be to try to kick it out. Just slightly nudge it and go into this regime. And then whenever you're in the excited state, you're almost guaranteed to escape. And if you're in the ground state, you don't escape. And what you do is you detect this escape. How do you detect the escape? Well, if you just had this, what you would do is once you escape, the phase particle, remember, it starts dropping down the washboard potential. It just starts rolling down. And so phase starts changing with time. There's nothing to stop the phase. And in terms of Josephson relations, this means that you get a voltage. So what you do is you send a current pulse and then you start measuring whether you have a voltage or not. This would be the readout. If you have a voltage, you are in the excited state. If you don't have a voltage, you're not in the excited state. This works, and it's easy to understand, this method. It is not so practical for doing qubit experiments. And that's because voltage means dissipation. And it will take a while to stop this particle to cool the qubit back down into a quantum state. You'll have to tilt the potential all the way back to stop the particle from jumping, and then tilt it back to this point where you have well-defined levels. So that takes time, and that's just not practical. So what you do is you add an inductor here, you short the two electrodes, and to that voltage, to that washboard potential, you add a parabola, and you just have two wells. One shallow well with two levels, and the second well is very deep. Now, the energetics of this circuit, the potentials are exactly the same now as for a flux qubit. Two wells, tunable by flux, flux through the loop. It's a loop with a Josephson junction. Very similar, but very different because the two quantum levels are in this one well, which is very shallow. And in the flux qubit, we had them between the two wells. But this second well in this circuit is for readout. So when you're in the excited state here and you nudge it and you escape, you just go here. And what all that does is it flips the direction of flux through this loop from left to right. So all you have to do now is detect whether the flux in this loop is left or right. And that you know how to do. From flux qubits, you build a readout squid and measure the magnetic field here. Yeah. So now we're back to exactly the same circuit, actually, as in the previous slide. But the quantum states are very different. I can't even explain to you what the quantum states are in this qubit. Their phase, I don't have an analogy for you. But the experiments are very similar. Qubits can be quite a bit larger. I already told you this. This is a micron-scale niobium circuit. But the protocol is very similar. This is it, again, on the chip. This is the chip that you can hold in your hand, and you can see that the qubit occupies a fair chunk of that chip. So you can see it with your naked eye, this quantum circuit. This is a beautiful graph. I really like it. What they do here is they constantly bias this squid up to switching current, and they measure where it switches into the voltage state. So they measure the supercurrent of this squid. And because it is dependent on the flux in this loop, and the little flux is created by this loop that it's coupled to, there are two very distinct switching points, which correspond to left circulating current in the red loop over there, and the right circulating current. So the two switching distributions are completely separate, and that tells you that in a single shot, in a single measurement, you are able to identify whether the qubit, the red loop, is in the ground state or in the excited state. So this graph is the evidence of single-shot readout. The overlap between the two distributions is tiny. So from one shot, you are sure about whether you're in the 0 or in the 1 here. And this is the protocol for how you operate this circuit. You remember, for any quantum computing algorithm, you have to start in a well-defined state. So in a ground state, for example, you start with no flux, and then you go to this point where you have the well-defined states. And if you do it slowly, you always stay in the ground state. So you always prepare the ground state. That's called adiabatic ramp. Then you apply some microwaves to prepare any superposition of 0, 1 that you want. Just like for a spin, just like for a flux qubit, the same technique. And then this little pulse is the nudge, the readout. So we prepare arbitrary state, and then we try to read out whether it's the ground state or the excited state. And we had two different rates. So then on the readout squid, nothing was happening while we were doing all that. And once the flux in the loop changed, there is this jump. And whether the jump happens here or here tells you whether the qubit was in the ground or the excited state, whether this flux was left or right. So by performing that experiment, you can do, again, coherent oscillations. In this case, this is, I'm not showing you a Rabi oscillations, but a Ramsey experiment. Remember, for Ramsey, you tilt your spin or your qubit into the xy plane of the Bloch sphere, and then you let the arrow evolve, and then you go back to the z-axis for readout. So you have to do two pulses, which are called pi/2 because of the angle by which you rotate. And in between, you have free precession. So for this phase qubit, you can observe many, many oscillations of free precession of this quantum state. So this tells you that you can observe, resolve many free evolutions of this quantum system before decoherence takes over. Okay, so now there are many beautiful experiments that were done with this qubit. They have performed full quantum state tomography. of these qubits. They have also gone through their own Moore's law of improving coherence. They have coupled multiple qubits. This will be a subject of one of the next lectures. Here I want to show you maybe the most beautiful experiment that they've done. And this is a kind of an application of this qubit. And it has to do with, I think this is the experiment that comes closer to realizing the Schrödinger cat experiment that we all know from quantum mechanics. So what they do here is they couple this qubit to another quantum system, and this is a mechanical resonator. It's been a holy grail in the various fields of physics to observe the ground state of motion. So to cool something down so low that you only see quantum fluctuations of motion, and you don't see thermal occupation. So if for a solid state system, this would be like having 0 phonons in your circuit. If you have a beam, for example, trapped between the two supports, this would be like a beam moving like that, having that mode, and then completely cooling down that mode, so there are no phonons in this mode, and the mode only fluctuates quantum mechanically with a half an h bar omega. So the quantum fluctuation, you cannot remove that, but you can remove all the phonons if you are very careful. And so actually removing phonons is very easy. Just cool it down low enough, isolate. There's actually no problem. What the difficulty is to prove that there are no phonons, to measure a state of 0 phonons, and then maybe controllably add 1 phonon, 2 phonons, and no more. And why that is hard is because of what I said in the beginning of the lecture. Coupling to environment is the problem, except when you try to measure, the strongest coupling to the environment is the coupling to your measurement apparatus. Whatever detector people tried to create to detect a 0 phonon state added a bunch of phonons in the circuit. So for example, in Delft, I worked with a carbon nanotube that was suspended and was vibrating. Yeah, we could put it in a dilution fridge, and the temperature in a dilution fridge is equivalent to a frequency of some less than a gigahertz. So if the resonance frequency is 10 gigahertz for this tube, of course we have 0 phonons in this tube, that's for sure. But as soon as we try to measure it by, for example, passing a current through the tube, that was not my experiment, but in my group, we put about 100 phonons in this tube. So the quantum regime was inaccessible. And that was a problem in many different experiments. And so here, a beautiful application of a qubit, in this case a phase qubit. And the idea is that goes back to the beginning of the lecture, the nonlinearity. So qubits are nonlinear systems which are extremely sensitive to very small signals because they decohere them. That means that if we isolate this resonator very well, but only couple it to 1 qubit, a tiny, tiny change in the motion of a resonator will be hugely amplified by the nonlinearity of the qubit and can flip the qubit. So coupling that we can achieve between this nonlinear system and the quantum system with the resonator is actually very large. And that enabled the experimental observation of the ground state of a circuit. This was a breakthrough of the year in science in that year, 2010. So this was a big deal because this is like looking at the Schrödinger cat state, if you wish, because this is a fairly big circuit. So this is a vibrating cantilever. They cooled it down. They hooked it up to a phase qubit. The circuit is exactly like this. Here is a qubit. It's an LC resonator with a Josephson Junction. That's what the phase qubit is. This is a mechanical resonator. So, for example, this capacitance, Cm, it is modulating with time as it vibrates. And so having this circuit here is like putting an AC bias on this qubit. because this AC capacitance will induce AC charge here. So it's entirely a circuit measurement. And then this AC bias, when it's on resonance with the qubit, it can flip the qubit. Here's the data. This is the qubit resonance, and here it goes through anti-crossing. Seen a little bit better here, just zoomed out on that region. This is the mechanical resonance frequency of the resonator, and it's picked in a range, in a good range, gigahertz, the same range. And this is the tunable qubit resonance, and when the two are on resonance, we have the anti-crossing. Tells you that the qubit is coupled to the mechanical resonator. Then they went through some thorough analysis of their data to prove that the resonator is in the ground state. I actually don't show that data here. What I want to show you is they tune to that anti-crossing, and they just sit there and they observe the oscillations. So what the oscillations are the oscillations between the two levels here. So once again, what they do is they sweep the qubit onto the resonance frequency of the mechanical oscillator, and they wait for a variable time when the two are on resonance. And what they observe in the readout of the qubit is these oscillations. Now, when the qubit oscillates, that means that the state of the qubit changes from up to down in a periodic fashion. But what drives that change is a coupling to a mechanical degree of freedom, which is itself in a quantum state, in a quantum ground state. So it only has quantum fluctuations and nothing else. So what happens when the qubit is swapped from up to down? There's some quantum is emitted from the qubit. And this quantum is emitted into the resonator, into the mechanical resonator. So the meaning of this data is swapping of a phonon in and out of the mechanical resonator and exchanging that information, putting it in the qubit and going back. So creating a phonon out of nothing from the excited state of a qubit. Then the qubit goes into ground state, and the resonator goes into the excited state with a single phonon. That is the meaning of these oscillations. Swapping of a quantum state between a mechanical system and an electrical quantum system. So the proper language to talk about these oscillations are vacuum Rabi oscillations. Because all we're doing is bringing the qubit on resonance with nothing, with vacuum, with some mechanical mode that is empty. And what the qubit does is it dumps its information, its quantum state, into that mode. And then we can retrieve it back. So this is quite amazing. Okay, now I'm going to switch gears for the third time on you. I apologize for that, but I warned you at the beginning that this will happen. We have talked about a flux qubit and a phase qubit. And a phase qubit is the most weird one to me, and the most beautiful one. Okay, I will not have a preference. I like them all. Flux qubit is also beautiful. This one is ugly. No. This one is also wonderful. I'll tell you why this one is also bizarre, though. So on the surface, charge qubit, already clear from the name, superpositions of charge states, like a charge on this place of a capacitor and this plate of a capacitor. This kind of superpositions. This is why it's bizarre. Because this is a superconducting circuit, the island on which we keep the charge is a little bit strange. First of all, charge is quantized in units of 2e. Why is that? Cooper pairs. That's right. So charge is quantized in units of 2e. Okay, it's a little bit strange. Yeah, we have a gate like in a semiconductor circuit, and we sweep this gate, and we add charge to this island from the gate. but charge jumps in pairs. They don't want to go one by one, they jump in pairs. That's because if we put only one electron on this island, we have to pay the superconducting gap energy, which is very large, hundreds of gigahertz or terahertz. Okay, but there is a second reason why this is a strange island. Remember, I told you about semiconductor islands. They're coupled by tunnel barriers, by capacitors. This one is coupled by Josephson Junction. Josephson Junction is an element through which a supercurrent can flow. Current without any dissipation can just flow here. Yet, in this circuit, in this dark square, there could be charge quantization. Yeah? I think it is a little bit counterintuitive. So in principle, it's connected by a Josephson junction with a zero resistance, supercurrent. Remember, we needed to have some quantum of resistance separation in order to talk about the well-defined charge before. Now I tell you zero resistance connects this island, yet we can have charge quantization. Well, the reason for that is, I can describe it in such a mysterious way, but the reason for that is relatively simple. It is the fact that charge on this island can be only in Cooper pair form, 2e, and that's a microscopic quantum coherent state. And then if the charging energy of this capacitor is large enough, it will cost you too much energy to put an extra Cooper pair on this island. And therefore, even though there could be zero resistance for these Cooper pairs, they just don't want to go there. So once again, from the energetics of this system are the charging energy is very large. So we have all these parabolas, and they're offset by 2e. And this is just a periodic degenerate potential, offset by 2e. But we also have a Josephson junction, a Josephson energy. When the charges are degenerate between -1 Cooper pair and 0 Cooper pairs, here in the middle, the system cannot tell whether it prefers -1 Cooper pair or 0 Cooper pairs on the island. And at that moment, Josephson current can flow through the island. The charge is at the degeneracy point. And so at this point, Josephson energy induces coupling between these two quantum states. And you can see that the Josephson energy is smaller in this case than the capacitance energy. These are a couple different calculations for the system for different Josephson energy. So for 0 Josephson energy, very simple spectrum, a bunch of these parabolas overlapping higher and higher. But if we just focus on the lower two, they just cross. And when we apply Josephson energy, there are couplings between these parabolas. The states of this qubit are, once again, the two lowest energy states in this system. And these would be 0 or 2 extra charges on the island. So this is the preferred charge, call it 0, and this is 2 more electrons on the island, cost you energy. This qubit was demonstrated, actually the first of all these qubits, in 1999, quickly followed by a Flux qubit. What you do here is you sweep through the anti-crossing between 0 and 2 Cooper pairs, and you go back and forth. At this degeneracy point, you observe swapping of charge in and out of the island. So similar to the previous procedure I described to you, but now with charges. The diagram is, once again, it's aluminum technology with shadows, and this graph shows coherent oscillations in color scale of charge on and off the island. Now this qubit is actually, of all the qubits was demonstrated first, it is also the worst. It's the worst qubit. Why is that? Who can guess? Coupling to... Okay, yeah, so that's a little bit general, right? Because every qubit becomes bad when there is coupling to environment, which leads to decoherence. But why is charged qubit worse than others? Well, magnetic interaction is also long range. Any more guesses?
Did you have very few electrons?
Yeah, so roughly along those lines. So basically, the point is, the difference is just adding a couple of electrons on this island. And this circuit is built on a substrate, which is a piece of semiconductor, which has a bunch of charges in it. Charges can live on the surfaces of these metals, and any charge jumps around this circuit immediately translate into decoherence, because it shifts you along this axis and changes the gap, the separation between the levels. So it changes the coupling rate, the precession rate, and leads to dephasing that you observe. And charge noise is, in general, is the worst noise of all. So it's not that the coupling is stronger or weaker, it's just that charge noise is the hardest to suppress. And so flux qubit, for example, which is completely insensitive to charge because the charging energy is small, or a phase qubit, which is nominally insensitive to charge, but in practice is actually sensitive. Those are better qubits. So for a phase qubit, it's a huge Josephson junction, so the charging energy is very small, but inside the junction itself, you're going to have a bunch of charge imperfections, traps, and charges jumping inside the qubit, inside the junction, and leading to a fluctuating supercurrent. So that limits that qubit. Flux qubit is limited by flux noise, by fluctuating spins, like I told you, cell phones, anything that creates magnetic fields. But if you do some shielding, RF shielding, magnetic shielding, you can remove all those effects. But it's very hard to remove charges which are jumping just underneath your qubit. And all materials have charge noise. This is also the reason to work with spin qubits rather than charge qubits in semiconductors. Once again, charge in semiconductors is also very hard to keep coherent. But spin, insensitive to charge, can stay coherent for seconds, very long. So charge qubits are a bad idea, even though they were beautifully demonstrated the first. Now I'm going to tell you that charge qubits are the best. Remember that Moore's law plot, what David DiVincenzo put together with qubits going up and up and up and up and up. Those upper points, those were almost entirely charge qubits, or qubits derived from this concept. But you have to tweak it. So here comes the transmon. Transmons are now the leading superconducting qubit. Here is a difference. Difference is visual. This is the charge qubit that I was talking about, that it was really bad. It's an island with a little loop. This is for tuning the Josephson energy, and this is for coupling to microwaves. So it's a little pad. This one's really bad. This one's really good. This is a 5 micron scale. This is a 100 micron scale. That guy, this Cooper pair box, is in here. It's there, trust me. It's this guy. And what are these things? Big wings. Blue is the metal. They are the two capacitors. Yeah, there's a capacitor. It's a huge capacitor shown schematically here. So it's a charge qubit, but with a huge capacitor, so the charge fluctuations become irrelevant. So they realized that they were doing all these experiments, and they realized we're limited by charge noise. So let's add a huge capacitor and take the charge noise out of the equation. This is what that capacitor does to the energy levels. On this side of the graph, I show you again the plot that I already showed you for the conventional charge qubit, the Cooper pair box. We have the overlapping parabolas. Because charging energy is large, capacitance is small. These parabolas are very steep. There are anti-crossings in these parabolas induced by the Josephson coupling. And the quantum levels are these two levels. Now I give you a visual interpretation of what charge noise does. What charge noise does in this energy diagram is shifting along this axis, shifting. So you can see that, okay, there is a little bit better point to operate the qubit here. Maybe it's a little bit less sensitive to fluctuations, but to the next order still is. But for example, if you're here, you have a charge noise, the energy level distance fluctuates like crazy. So the difference between these two, if you are here and you have some noises. So this is the problem that they were trying to address. This is what adding a large capacitor does. Pretty much these levels become flat. It's insensitive to charge noise. The capacitance from the transmon is making the ground and the excited state completely flat along this axis. This is seems like it solved the problem. It did. The qubits work wonderfully. I will show you in the next lecture how well they work and what experiments they enable. But now let's spend the last minute or so thinking about what have we done? What is this qubit now? It was supposed to be superpositions of charge states, and what was creating these superpositions was the fact that we had a very large charging energy, and so there was a difference between having one Cooper pair and two. Well, now by adding this capacitor, we kind of removed it, so we have these levels. They are almost equidistant, just slightly anharmonic, and so all the concepts that I told you about in this lecture are kind of cancelled in this qubit. It is to me, it's almost a classical circuit. It's a big capacitor with a tiny, tiny Josephson Junction element that makes it slightly anharmonic. This is what it is physically. It's a capacitor this size with a little Josephson element. Capacitor is a completely understood linear circuit, and a tiny nonlinear element enables all the qubit work with these systems. So in the end, the resume of the lecture is that all we needed to do to create the best, the most robust qubit is to take a classical circuit, make it slightly nonlinear, and that is called a transmon. Transmon is the best superconducting qubit to date. And here I stop, and next lecture we continue with transmon experiments.